Good afternoon, everyone. Thank you for being here. My name is Ankur Arohi. I'm strategist at emsys Grid Services and an alumni from RWTH Aachen. Today, we were thinking for a while, what should we present at LF Energy? Because our journey with LF Energy has been also long. We have used a lot of open source tools, and we thought, okay, we would provide some stories on the industrial application side of the open source tools. So mixing and bridging the gap between the technical side and the business side. And our business case is forecasted congestion management using plug-and-play model. So just a quick view of who we are, what we do. So we are located in the northwest of Germany, in Oldenburg. And we are a conglomerate of 3 companies, emsys, VPP, the grid services, and the systems. So in terms of market share, we have 50% of the worldwide installed capacity of wind and solar predicted through our systems, which goes into a virtual power plant setup. And we have transitioned into the grid service business. That's where we say we have put our hands into the electric network. And here we are dealing with forecasting the network state for more than 50 grid operators currently, mostly in the German region. And we are looking to also extend the services around the world. What we basically do is, apart from forecasting the states of the network, we also forecast the congestion in different use cases for day-ahead markets. And we materialize the regulatory requirements, for example, the redispatch 2.0. For the guys who don't know about redispatch 2.0, this is an innovatory, I would say, regulatory requirement which deals with the installed capacity of power plants being more than 100 kilowatt. They all must actively participate in redispatching. So that means also the DSO takes a very active role in the whole landscape of redispatching. And if we move to the challenge, so the challenge is huge, because if you see on the left side, we have so much distributed generation that even if we have valid forecasts of the distributed generation, the model is so undeterministic and so dirty that we have an additional layer of complexity on the complexity of the network itself. That means if we need to forecast the network, we need to be able to, of course, import the CGMES, which in itself is a big task, considering the uncertainty on the CGMES side. Then we need to be able to import the switch states or the remedial actions already planned. We need to be able to correctly forecast the aggregators and the states of the systems. And on top of that, we need to run power flow. Well, that's not the end of the story. We still need to optimize the network in order to create our own optimized schedules, which would be the remedial actions. So this was the plan back in 2022, I would say, or till 2022. We were using one single source of truth, which was the pandapower solver, and our inbuilt Neo4j graph database. So what we were doing was we were importing the CGMES into a network X structure based on Neo4j, which was good. But then here comes the truth. Were we happy with that? No, because most of the problems were around the use case. We had a very interesting use case of wide problem. Our problem was not one customer, so it was not just a TSO or a DSO. We had a mix of TSOs, DSOs, and some DSOs which had TSO networks modeled in their SCADA software, which were also exported into the CGMES format. So this was really challenging. And because of this wide problem and uncertainties at the input and forecast layer, the network was not very robust, and the solution also not. So what was the problem? The problem was failing production readiness. So every problem comes up with a possibility of creative ideas which could lead to innovation. What was that in our case? Our strategic aim was very clear. We cannot afford no CGMES import, because that would mean we don't have a network, we cannot integrate any forecasts, and we cannot provide any remedial actions. So we cannot simply ignore the CGMES, even if it's dirty. That's a mammoth task. On the other hand, we also have we don't have the possibility to build and patch everything. We cannot patch all CGMES structures and failing exports from SCADA software. So what do? We thought, okay, we need something similar to a USB. What do we do when we connect a USB to our systems? We don't expect that it crashes. If one driver fails, we expect we would have another driver which would read it. And we wanted to use this analogy. What we did was we created a synchronized landscape of multiple importers and validators, which I'll present. So our solution statement was, we do want flexibility and mature features. So we do want to tap the open source world. We don't want trial and error. We are not going to look for all use cases of failing CGMES import. And we know if CGMES file is invalid, regardless of which tool you use, it is invalid. If you use powsybl or PGM, if a CGMES is invalid, it will stay invalid. So what do we do next? We also don't want adapter hell. We don't want to keep converting pandapower in PGM or powsybl to pandapower, so on and so forth, because that would mean one crashing system would destroy our pipeline. What do? We were basically focused on these 4 software. Pandapower was the one that we were using anyways. The second last is the VeraGrid that was presented by Josef right now. Before that, we had sessions on Power Grid Model and powsybl as well. So since a couple of years, we investigated all of these softwares, and we came up with a, we came up with a benchmarking. That means we came up with kind of a Monte Carlo simulation of all the possible scenarios that we will face and we are facing. And we understood quite early that we need to have a validator. And these 3 adapters, because we knew that PGM was so nice that they created already an adapter to pandapower. So we just needed the bridge between powsybl and pandapower to VeraGrid. That would solve our use cases. I mean, most of them. So to eliminate trial and error, which is our next problem, what we had to do was to train or at least classify using an active tool, which we call clustering and classification tool. It's based on AI. So the output of this tool is, it provides us information based on the network structure and the attributes, which would be the right setting of import. Do I use powsybl? Do I use pandapower? Or we use our own in-house importer? What should be the right settings? Now, the thing is, if you import a network and you try to run load flow, if it doesn't converge, what do? Well, we try to change the solver and recheck it again. What if I would say that there is a tool which already tells you before which solver is the most optimum. This is something that we have tried to achieve. So before running load flow, I know that this DSO network with this attribute should use a decoupled LU solver and not a Newton-Raphson solver because of the experience. So that's what comes out of this tool. If we move forward. Well, I would not like to go into details of how we come up with this solution, but it's based on a classical Monte Carlo simulation-based classification and clustering problem, which is very common in AI world. In principle, we create different kind of clusters of the input, and we run supervised learning, including the feedbacks of previous power flow runs. And in the end, we have the optimum configuration. Now, additional to the optimum configuration, we do also provide the fallback strategy. So let's say if our initial plan fails, we should have a fallback, because this has to run in production environment. It just can't fail. So that means we need a self-healing system. What is that? So all of our platforms are Kubernetes-based. We run containers in Kubernetes, and well, that has to be configured before, which this offline AI tool helps in. And then we run the CGMES import, and we forecast the network. We see if that was successful. If it's successful, then, of course, that's a good case. If it's not, then we move towards the fallback, which we had already configured through the tool. Now, that's a very interesting aspect. We have introduced a Kafka messaging bus that already sends a trigger to another container which is already in standby. So let's say I imported the network through through powsybl, and for some reason it failed. Well, it doesn't happen quite often, but let's just assume this case that it failed. I do have another container which is already running and on. So if I send a Kafka message and I invoke this, let's say pandapower or our in-house importer, it picks up from the point that the powsybl failed and tries to convert the CGMES. That's the idea. So that's what I try to explain. So we have multiple containers which are already in standby states, and depending on the Kafka message and event sending system, which is all in real time, we do have the capability of plug and play any open source tool that we want, which we find useful and which works for that network. Well, but there are still some cases where that also fails. In that case, we have no other option but to inform the client that there are some issues, and we do log such issues. I want to share some real-world stories about how that worked. So we had a mysterious West German DSO outage challenge. So this was really interesting because we tried to import the network. Import was okay, and we tried to compare the network details. That also looked fine. But then when we tried to run load flow, we had issues. And we really couldn't figure out where are the issues. It was simply not converging. So we trained the AI model in such a manner that the fallback strategy told us or informed us that it would be nice if we simply use a PGM solver, and it actually worked. So we used a PGM solver and used some of the manipulations, and we could see that the network was at least converging. Now the quality is something else of the results, but at least it doesn't break. And then there was another example that I can bring in from Bavaria. So there was a state estimation issue. We knew that the network is already challenging because the Rx ratio is a bit off, so the R value is high, and we needed something very powerful, something which is close to research, let's say, and that was VeraGrid for us because we could really debug and see where exactly the failure is coming, and we were able to manipulate the values, which we also informed the client then. And that goes in the feedback loop for the AI tool as well. And that's how one new tool is born, which we call collaborative plug and play. And we would love if we find more active collaboration to that tool. The best thing is we will open source all of that, including the AI tool, in this call PNP. So how can you contribute to call PNP? So that's my pitching statement. I have a contrarian view. Instead of looking at one tool and solving this tool for perfection, well, perfection is another thing. It's a perspective. We do suggest that we should go a bit more API agonistic and look at the landscape. There are very nice tools also there. For example, VeraGrid, very powerful. And it's really important that people also look to such tools and try to bridge the gaps. And that also opens up new strategies like plugging in APIs for Power Factory, for example, or other tools to share the results, even for comparison purposes. If you would like to contribute, you can scan in this barcode that will take you directly to our GitHub page. And we will be creating roadmap for the coming years to keep developing this tool. Our vision is to make the AI tool so powerful that it should be able to manipulate the failures automatically after CGMES conversion so that the production environment is not failing. And that would be it. Thank you. Any questions? Oh, please. So there are many things that can go wrong with CGMES. So especially the use case that we have a data model which has in transitory region of TSO network that adds so much complexity that the data that we have in the network model is not accurate anymore. So we have, let's say, trafo tap step position which is completely off because TSO didn't inform DSO or DSO didn't use the recent ones, and then it doesn't match with your forecasted model anymore. So yeah, it could be anything, and it was really for us very difficult to find out where the failure is, because it could also be in the software which exports from SCADA to a CGMES. For the operator, everything's working fine, but for us not. And then it's very difficult to find out where the problem is. Any other question? Okay, so thanks a lot.